Hello, I'm Daryl Thrasher. Today I'll be going over a presentation of analytics on the edge using the Macondo Deepwater Horizon incident as a basis. 126 workers on the BP Deepwater Horizon were going about the routines of completing an exploratory oil well, unaware of impending disaster. The loss of control of the Macondo well, the resulting explosion and fire resulted in loss of life, a spill of nearly 5 million barrels of oil, and approximately $60 billion in damages and lost value. With this presentation, Lone Star will demonstrate the capability to use both synthetic and real-time data to operate high-value, advanced analytics at the network edge on gateways that will focus on the predictive cumulative risk impact of decisions leading up to the day of the incident. The gateway will be running on a bowtie risk model generated in AOS Architect and loaded into an HP EL20 gateway running AOS Edge, and based on decisions and data from the President's report regarding the incident. Geologic conditions, casing selection, seaman design and test result decisions will be displayed on the left side of the screen. The processes to be monitored during the cement job and to verify the cement job prior to temporary abandonment are shoe track conversion, positive and negative pressure test. The results of 1,000 Monte Carlo simulations from IoT Gateway will be displayed on the right side of the screen in real time. As decisions and processes deviate from design expectations, the predicted results of these decisions will increase the probability of a blowout. Of two indicators, one is the nominal probability of a stochastic spread, and the other is the possible high of a stochastic spread. The bottom two risk indicators are process monitors that represent what the crew would be seeing as the processes are being executed. These are indicators of the sensor readings that deviate from the upper and lower control limits and will turn red as sensor data exceeds these limits. The effect of these deviations will be also seen in the blowout probability risk indicators. After the rig crew lowered the casing into its final position, a specialized cement blend would be pumped down inside the casing string and then flow out of the bottom and up into the annular space between the casing and the sides of the open hole. Once cured, the cement would seal off the annular space and isolate the hydrocarbon-bearing zone from the inside of the casing itself. The design team on shore had three decisions to be made prior to the cementing process. One, which production casing to use, long string versus liner. Two, the number of centralizers for the casing. And three, the cement slurry design and test results. BP's design team originally had planned to use a long string production casing, a single continuous wall of steel between the wellhead and the seafloor and the oil and gas zone at the bottom of the well. However, after a lost circulation event, they were forced to reconsider a shorter string of casing anchored to the next higher string. A liner would result in a more complex and theoretically more leak-prone system, thus increasing the risk of a blowout. A cement slurry must be tested before it's used. When testing a slurry that will be foamed with nitrogen, the lab also evaluates the stability of the cement that results. A stable foam slurry will retain its bubbles and overall density long enough to allow the cement to cure. If the foam does not remain stable up until the time the cement cures, nitrogen can break out of the cement, with unpredictable consequences. Based on these critical decisions, the risk context has changed from a 0.0004 probability of a blowout to 5% nominal probability and possible high of 13%. The crew was not aware of this change in the risk context based on these decisions, and their reaction to the risk context was inadequate. The design expectation was that 600 psi would establish cement flow into the well. Even when pumping fluid at 1800 psi into the well, the crew was unable to establish cement flow. At that point, the rig team decided to increase the pump pressure in discrete increments, hoping eventually to dislodge the autofill tube. On their 9th attempt, mud finally began to flow. Significantly, however, the pump rate of mud into the well and through the chute track thereafter never exceeded approximately 4 barrels per minute. The team concluded that the flow valves had converted. The first step in the temporary abandonment was to test well integrity, to make sure there were no leaks. The positive pressure test evaluates, among other things, the ability of the casing in the well to hold in pressure. Much like pumping air into a bike tire to check for leaks, the rig crew pumped fluids into the well to generate pressure and then checked to see if it would hold. They pressured the well up to 250 psi for 5 minutes, and then pressured up to 2500 psi and watched for 30 minutes. The pressure inside the well remained steady during both tests, showing there were no leaks in the production casing through which fluids could pass from inside the well to the outside. The negative pressure test checks not only the integrity of the casing, but also the integrity of the bottom hole cement job. At the Macondo well, the negative pressure test was the only test performed that would have checked the integrity of the bottom hole cement job. Now, the crew would eliminate pressure inside the wellbore to 0 and see if it remained at 0. Sensor readings inside the wellbore increased, so a second test was performed using the kill line. The rise in pressure in the wellbore was attributed to bladder effect. First, the crew sets up the well to simulate the expected hydrostatic pressure. Second, the crew bleeds off any pent-up pressure that remains in the well. Third, the crew and the well site leaders watch to make sure that nothing flows up from and out of the well and that no pressure builds back up inside of the well. The crew made a key error and mistakenly concluded the second negative pressure procedure had confirmed the well's integrity and moved on to the next step in the temporary abandonment. At 9:01 p.m., in the middle of a shift change, the drill pipe pressure in the wellbore began slowly increasing and went unnoticed by operators. From 9:40 p.m. to 9:43 p.m., drilling mud began spewing from the rotary into the rig floor, and the crew realized that a kick had occurred. At 9:40 p.m., efforts to mitigate the kick were futile. Gas was already above the BOP, rocketing up the riser and expanding rapidly. Ignition and explosion were all but inevitable. The first explosion occurred on the drilling floor, and the Macondo disaster claimed its first victims. A dramatic and tragic event that illustrates the power of predictive and prescriptive analytics performed at the network edge on gateways that assesses cumulative risk and the significant decisions facing companies and stakeholders across all industry categories. Lone Star is unlike any other provider. We invite you to consider the unique resources and solutions available to you from Lone Star and the human and revenue benefits of prediction and prevention. Thank you.